Okay, so what you guys learned about logarithms last time, or what we've been learning about last week, was how to solve logarithms and how to change between logarithmic and exponential form. Now we're going to look at solving equations that have logarithms in them. And so to do that, there are some properties of logarithms that you'll need to know. The first one is this. If we have log base 5 of x equals log base 5 of 8. So if log base 5 of x equals log base 5 of 8, then what does x equal? 8. So if you have two logarithms that are equal to each other, as long as they have the same base, then whatever is in this position and this position have to be equal. For example, log base 2 of x squared minus 4 equals log base 2 of 3x. These two logarithms that are set equal to each other both have a base of 2, which means x squared minus 4 has to be equal to 3x. So we can set x squared minus 4 equal to 3x in order to then solve for x. Now to solve this for x, if you look, we have x squared and we have a term that has just x to the first power. If you see those two things, most likely you'll have to solve the quadratic equation. So in order to solve that, we want to get everything on the same side and have it set equal to 0. So if we subtract 3x from both sides, we have x squared minus 3x minus 4 equals 0. Okay, hopefully you remember how to factor a quadratic. When you factor a quadratic equation, you're going to have two sets of parentheses. The square root of the first term is what goes at the front of both of these sets of parentheses. So the square root of x squared, which is just x, is what's going to go at the front of both of these sets of parentheses. Then you're looking for two numbers that multiply to be -4 and add to be -3. So factors of -4 that add to be -3 should be -4 plus 1. Because -4 times 1 is -4, and -4 plus 1 is -3. After you get your two factors, you can set each factor equal to 0 separately and then solve for x. So we've got x minus 4 equals 0 and x plus 1 equals 0. Add 4 to both sides here, we get x equals 4. Subtract 1 from both sides to get x equals -1. So we have two answers here. We do have to go back and check to see if these are going to be actual solutions to the original equation. In order to check, we're just going to go back to the very first line and plug in these values for x. So if we're checking x equals 4, then we have log base 2 of 4 squared minus 4 equals log base 2 of 3 times 4. So all I did was take the very original equation, I plugged in 4 for x. So we can simplify this a little bit here. 4 squared is 16, minus 4 is 12. And then 3 times 4 is also 12. So when we use the property that says if you have two logarithms set equal to each other and they have the same base, we can set 12 equal to 12. And because that's a true statement, 12 is equal to 12, then x equals 4 does work as a solution. So we're going to go back down here and circle it. That just shows me that, yes, we got x equals 4 as an answer, but we've done the work to check and make sure that it's a solution. So we circle it. Now we're going to plug in x equals -1. So we got log base 2 of -1 squared minus 4 equals log base 2 of 3 times -1. Do the little bit of math. -1 squared is +1, minus 4 is -3. And 3 times -1 is also -3. Now pause right here, don't write anything else. We got to talk about something. So on the surface, this looks like it's going to work. We're not going to write it, but normally if we did the exact same thing we just did to check x equals 4, we would say -3 equals -3, that checks out. But we have an issue. If you look at your calculator, if you press math, it's going to bring up this list of functions. If you scroll all the way to the bottom, or almost the bottom, there's a function called log base. If we press enter to use this function, we can plug in any logarithm. So what I'm looking at right now is log base 2 of -3. So plug those numbers in, press enter, we get an error message, non-real answer. Okay, what's happening is, if you look at this logarithm, log base 2 of -3, if we were to say, you know, what question is this logarithm asking? Well, it's asking 2 to what power equals -3? There is no number that we can put as an exponent here, no real number at least, that would then give us a negative answer. Because all we're doing here, when you raise 2 to a power, is you're multiplying 2 times itself, however many times you put up here. 2 times 2 times 2 times 2, and so on. That's never going to give you a negative number. So when working with logarithms, the number that is in this position cannot be negative. So because plugging in x equals -1 gives us a negative answer or a negative number here, that means x equals -1 cannot be a solution. So we're going to say.
So what if one's negative and one's not?
Then it still is shuts you down. Yep. Yeah, it worked out this time to where they were both negative, but even if one or the other were negative, that would stop you in your tracks. You would not be able to use that x value as a solution.
Then if you do it and the numbers are different, it's nothing.
Correct. Yeah, or maybe you did something wrong when you were working the problem. Any questions so far? Any other questions? All right, let's look at another one. Log base 4 of x squared equals log base 4 of negative 6x minus 8. Okay, so we have two logarithms set equal to each other. Because they have the same base, we know x squared has to be equal to negative 6x minus 8. Then we want to solve for x. So again, because we have x squared and a term that has just x, the way that we're going to have to solve is by getting everything on the same side of the equal sign and factoring. So I'm going to add 6x and add 8 to both sides in the same step. So we get x squared plus 6x plus 8 equals 0.
So when you're doing that and there's the negative in parentheses, like the negative 6 and blah, 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 and then you make them positive.
Yeah, because we're trying to move them to the other side of the equal sign, we do the opposite of whatever they are. Yeah. And the reason we want to move both of these numbers over here instead of just moving the x squared over here is because if we were to try to move the x squared, we would have to subtract it from both sides since it's positive right now. And that would give us a negative x squared. And you can't factor into the two sets of parentheses when your x squared term is negative. So we want to keep x squared positive. So now we can factor. We have two sets of parentheses. We know that x goes at the front of both of those. Then we're looking for two numbers that multiply to be 8 and add to be 6. Say again? 4 and 2, yeah.
I thought you had to have the same number.
These had to be the same?
No, I was thinking like that they had to add, the same number had to add going to 6 and I don't know what else.
That's fine. Yep, 4 times 2 gives us 8 and 4 plus 2 gives us 6. So plus 4 plus 2. Then we're going to set each of these equal to 0 separately. And solve for x. So we get x equals negative 4. And x equals negative 2. Okay, let's check our answers. So we're going to check x equals negative 4 by plugging negative 4 into the very first line of our problem. So we've got log base 4 of negative 4 squared equals log base 4 negative 6 times negative 4 minus 8. Okay, so this first part, it says log base 4 of negative 4 squared. So this negative makes me nervous at first. It should at least pop out at you that there's a negative where we just said you're not allowed to have a negative in a logarithm. But we're not just taking log base 4 of negative 4, we're taking log base 4 of negative 4 squared. So really what we're doing is taking log base 4 of positive 16. So we're okay there. Because the negative 4 is being squared, we can go ahead and take the next step because that gives us a positive 16. Again, on this side, there's a lot of negatives happening. That should pop out at you as a red flag, but let's go ahead and do this math and see what we get. -6 times -4 is a positive 24. -8 is a positive 16. So we didn't end up with any negative numbers once we did the math, which means we can go on to the next step to say 16 equals 16. So -4 does work as a solution. Circle x equals -4. Okay, same thing with -2. We've got to plug that in. -2 squared gives us a positive 4. -6 times -2 is a positive 12. -8 is a positive 4. So we didn't end up with a negative on this one either. 4 equals 4, that works out. So x equals -2 is also a solution. If you can fit it, I've got one more to work on this front page, and it's a lot shorter. It's probably half as long as the two that we just did. Yeah, just find some space anywhere on the front page, and then we'll take a break after this one. Log base 3 of 5x minus 1 equals log base 3 of x plus 7. Anybody recognize why this one might not be as long? Sort of. It does have to do with the x. It's that we don't have an x squared term. So we're not going to have to factor, which makes this a lot shorter. Okay, we have two logarithms that are equal to each other. And because they have the same base, we can say 5x minus 1 equals x plus 7. There's not an x squared, so we don't have to get everything on the same side. What we want to do is get all the x terms on the same side and everything else on the other side. So I'm going to subtract x from both sides to get rid of this x over here. And then I'm going to add 1 to both sides to get rid of this 1 over here. So now we have 5x minus x is 4x, and 7 plus 1 is 8. Now to get x by itself, just divide both sides by 4. And we get x equals 2. Check our answer by plugging that in. Do the math to make sure we don't have any negatives within our logarithms. 5 times 2 is 10, minus 1 is 9. And 2 plus 7, also a positive 9. And 9 equals 9. So x equals 2 is a solution. Okay, before we continue looking at some more properties, one thing to note is if the base of a logarithm is not written, it's understood to be 10. I'll explain what I mean by that. Up until now, we've worked with logarithms that have a written base. Let's say log base 2 of 8. We can see that the base is 2. But there may be times where the base is not written and you just have log of x or log of some number. If the base is not written, it's understood to be base 10. So just like we have the square root, even though the root is not written, we know that it's a square root. The root is 2, because any other root would actually have the number written, cube root, fourth root, fifth root, and so on. But if there's a square root that doesn't have a written root, it's understood to be 2. So with logarithms, if the base is not written, it's understood to be 10. That will come more into play from now on. Okay, let's look at the product property of logarithms. If you have log base b of a times c, this is equal to log base b of a plus log base b of c. So if a is being multiplied by c, we can break this up into 2 logarithms. The bases are still going to be b, but we split up the a and the c and we add those logarithms together. For example, log base 2 of 5 plus log base 2 of 6. This is how we'll be using this property to solve problems. If we have 2 logarithms that are being added together, as long as they have the same base, we can rewrite that as 1 logarithm with the same base, and we're going to multiply 5 times 6. So it kind of works backwards as what we listed when we did the property, but this is how we'll be using it, is to combine 2 logarithms that are being added together into 1. If you wanted to go the next step, you could say that's log base 2 of 30. Okay, the quotient property, if you have log base b of a divided by c, we can split this up into 2 logarithms, log base b of a minus log base b of c. So addition and multiplication go together, and then we have subtraction that goes with division. The way that we'll be using this property, let's say we have log base 2 of 5 minus log base 2 of 6. So now we have 2 logarithms that have the same base. They're being subtracted. The way that we're going to use this property is to combine these 2 logarithms into 1. So it's still log base 2, but then it's of 5 over 6. So whatever number is coming first is your numerator. Whatever number comes second is your denominator. So this becomes log base 2 of 5 over 6. And if we could simplify the fraction, we could go another step, but this is good enough for now. Last property is called the power property. We have log base b of a raised to the power of c. So c is now an exponent on a. We can move that exponent so that it is down in front of the logarithm. So this is c times log base b of a. So again, the way that we're going to be using this property is kind of backwards from the actual rule. Let's say we have 5 times log base 2 of 6. In order to use the other properties that we've talked about today, we can't have numbers in front of logarithms. So this property is going to help us get rid of those, because we can write this as log base 2 of 6 to the 5th power. We can move that 5 that's down in front as an exponent on the 6. And if we wanted to, we could find the value of 6 to the 5th power. It's actually 7,776. Any questions about these properties? So first of all, on the front page, we learned 2 logarithms that were equal to each other. As long as they have the same base, then you can set these numbers equal to each other to solve. The product property says if you have 2 logarithms with the same base that are being added, you can rewrite them as 1 logarithm using the same base, and you multiply. 2 logarithms with the same base that are being subtracted, you can rewrite as 1 logarithm using the same base, and you divide. And then the power rule says if there's a number in front of the logarithm, you can move it so that it becomes an exponent on this number. Because in order to use the rest of the properties, you cannot have numbers in front of the logarithms like this. Okay, I want us to stop here for today because we don't have enough time to work all the examples that I want to work. We'll work those tomorrow using the 3 properties that we just learned.